Alright, so still on past question review 2020-2021. We'll be attempting question. We are now on the third section, section 3, which is the final section. The first question, that's question 5A, says for the leakage of oil through a crack in a wall, assuming pressure builds up in flow direction, give a sketch of the shear stress distribution and the velocity profile. Okay. Alright, so the velocity profile and the shear stress distribution will be much at the point of the leak. So let's consider that we have a wall. I'm going to draw them together. Okay, this is a wall. Okay, this is a wall. All right, so this is a wall. This will indicate the, I will draw the velocity profile here. So if there's a leakage, let's just see there's a leakage somewhere here. Let's say there's a leakage somewhere here. The velocity profile will be much or greater at the leakage. So you have something like this. So this is the leakage. You have the velocity profile to be greater at the leakage. So you have a curve in this manner. Okay, so this is the velocity profile. It looks something like this. All right, so just manage that diagram. So you have something like this. So once you move away from the leakage, the velocity profile reduces once you move away from the leakage. So you have something like this. Okay, so it will be greater at the leakage, at the point of the leakage. Okay, so this is the leakage. That's the leakage. Okay, so this is the velocity profile. All right, the next says we should indicate the shear stress distribution as well. Similarly, let's, okay, still on this, let's make a straight line. The shear stress will also be greater at the leakage. Okay, so you have something like this. It will be greater at the point of the leakage. So you have something like this. Okay, you have this. All right. So this is the diagram for the shear stress. So this is the point of leakage, and you have the maximum shear stress there. So this is the shear stress distribution. All right, so that is it for that particular question. So we'll move on to the B part of the question. So question 5B says a container of oil with 1.8 poise and specific gravity of 0.85 has a horizontal parallel crack in its end wall, which is 500 millimeters wide and 50 millimeter thick in flow direction. If the pressure difference between two faces of the crack is 10 kilopascal and the crack forms a gap of 0.4 millimeter, question says calculate I, the volume of oil leakage per hour through the crack, II, the maximum leakage velocity, and the shear stress at the wall. Okay, so let's get down our parameters to that particular question. Let's start by picking out our parameters. So we're given that a container of oil with 1.8 poise. So that means the viscosity is given as 1.8 poise. Okay, so we'll start by viscosity mu, and take note, since it's in poise, it means it's dynamic viscosity. You have 1.8 poise. So we convert this to Newton seconds per meter square simply by multiplying 1.8 by 10 to the power of minus 1. So this simply means that viscosity mu is 0.18 Newton seconds per meter squared. All right, next parameter that was given to us, okay, and specific gravity of 0.85. So we're given specific gravity, okay, specific gravity S was given to us as 0.85, okay, has a horizontal parallel crack in its end wall, which is 500 millimeter wide. So width was given to us. Okay, the width B is equal to 500 millimeter. Convert this to meters by dividing through by 1000. You have 0.5 in meters. All right, next parameter that was given to us is and 50 millimeter thick in flow direction. So we're given thickness. Thickness was given to us, and the thickness is simply y. It was given as 50 millimeter. Converting to meter, divide by 1000. You have 0.05 in meters. Okay, so if the pressure drop between two faces of a crack is 10 kilopascal, so change in pressure drop simply means change in pressure. So change in pressure, that's dp, was given as 10 kilopascal, which is okay, 10 kilopascal. So dp is actually 10 kilo is by 10 to the power of 3 pascal. We have this to be dp, and the crack forms a gap of 0.4 millimeter. So take note now, the crack forms a gap. This gap is actually what? The length. Okay, this gap is simply the length of the crack. So length L, or you can use the X to be equal to 0.4 millimeter. So we convert this to meters. The X becomes 4 by 10 to the power of minus 4 in meters. If we divide 0.4 by 1000, it converts it to meters. Okay, now the first question says calculate the volume of oil leakage per hour. So we have to calculate the first question, volume of oil leakage per hour. All right, so volume per hour is simply discharge. Okay, the volume flow rate per hour simply means discharge. So we have to find discharge. Now, to find the discharge, we make use of the Hagen-Poisuilles equation for a viscous flow through a cracked wall, and that equation gives us that discharge. Okay, discharge Q is equal to, we have K y cube all over 8 mu dp all over the x. So this is the Hagen-Poisuilles equation um, for a viscous flow through a cracked wall. All right, so that's the equation for a viscous flow through a cracked wall. So if we know this now, where K stands, K depends on the geometry of the figure. K is a constant and it depends on the geometry of the figure. Now, in this question, we are given that this crack has a length and of course it has a thickness. So which means if I connect this together, that means this crack is actually what? Rectangular. Okay, rectangular. So K has different values for different structures. If the geometry of the shape, if the geometry of the figure is circular, K has a different value. But in this case, that we have a length and we have a thickness, so which means it's rectangular. Therefore, K, the value for K can be found using the equation YQ. 12 over y cube. Okay, 12 all over y cube, where y stands for the thickness, and of course, so this is now equal to 12 over y is the thickness, and thickness is 0.05. Okay, all to the power of 3. So I'll do this at once just to save time. So 12 divided 0.05 to the power of 3. This will give me the value of k. This implies k is equal to, so we have 96,000 for the constant k. So k depends on the geometry of the shape. So if you have, of course, a circular shape, if the crack forms a circular shape, you have a different value for k. So let's fall back to the equation. So all right, so this is the equation for discharge. Now we'll find the value of k. Y, of course, remains the thickness. Mu is the dynamic viscosity. Dp dx, of course, remains the pressure gradient. And we have all, okay. So the next thing to find is dp dx. So we're given difference in pressure. Remember from the question, we are given pressure drop, okay, or the change in pressure as 10 kilopascal, and then we are also given the length of the gap formed by the crack, which is 4 by 10 to the power of minus 4. So this will help us to find what dp dx. So take note, pressure with respect to what? The length. All right. So we can now find the PDX using the equation. The PDX is now equal to change in pressure give us 10 kilopascal, which is 10 by 10 to the power of 3 all over the x itself is 4 by 10 to the power of minus 4. So if we complete this, we are going to find that the pressure gradient, the PDX, is equal to 10 by 10 to the power of 3 divides 4 by 10 to the power of minus 4. So we have 2.5 by 10 to the power of 7. All right, so we now find our pressure gradient to be equal to, okay, we had dp over the x to be equal to 2.7 by 10 to the power of 7 newtons per meter cube. All right, so this gives us our pressure gradient. So if we know our pressure gradient now, we can now plug back into the equation. Let me recall the equation again. We have this charge to be equal to ky cube all over 8 mu times dp dx. So let's plug in all our parameters into the equation. This implies that this charge q is equal to, k is a constant, and we've obtained the constant for rectangular shape to be 96,000. So we have 96,000 multiplied by y is our thickness, which is 0.05 to the power of 3 all over 8 multiplied by dynamic viscosity gave us 0.18. Okay, the whole of this multiplies pressure gradient, which we obtain here as 2.7 by 10 to the power of 7. Okay, sorry, this is 2.5. Pressure gradient is 2.5. Okay, sorry for that error. Pressure gradient is 2.5 and not 2.7. So this is what we'll do now. So Q is equal to save time, let's multiply all through the numerator. 96,000 multiplies 0.05. So 96,000 times, open a bracket, 0.05 to the power of 3 multiplies 2.5 by 10 to the power of 7. Okay, let's multiply numerator all through. So that gives us, the multiplying through the numerator, we have 3.0 by 10 to the power of 8 all over 8 multiplies 0.18 gives us, that gives us 1.44. So now we do 3.0 by 10 to the power of 8 divides 1.44. So this implies that this charge is equal to 2.08 times 10 raised to the power of 8. So this charge gives us 2.08 by 10 to the power of 8 in meter cube per second. Now take note, this is in meter cube per second. All right, so we have our discharge in meter cube per second, but the question says we should find it in meter cube per hour. So you recall that 3,600 seconds actually makes 1 hour. So we need to convert this now from seconds to meter cube per hour. To do so, this is a very simple conversion. You have to be very careful with this to avoid errors. All right, so this charge Q is equal to, we obtained 2.08 by 10 to the power of 8 meter cube per seconds. This is now times. To cancel our seconds from here, you recall that 3,600 seconds make an hour. So you have 3,600 seconds, which makes 1 hour. Therefore, notice now that seconds cancels seconds. So we've been able to remove seconds and we're left with what? An hour. So that means we're multiplying to obtain this charge Q. We're actually multiplying 2.08 by 10 to the power of 8 by 3,600. This gives us meter cube per hour, and therefore this charge Q is equal to 7.5 times 10 to the power of 11. That gives us 7.5 by 10 to the power of 11 meter cube per hour. So this becomes the volume flow rate in meter cube per hour. Okay, so that's it for the first question. The second question says calculate the maximum leakage velocity. Okay, we are to find the maximum leakage velocity. So to find the maximum leakage velocity, we also employ the Hagen-Poisuilles equation for a crack for a viscous flow through a cracked wall. All right, so Vmax is given simply as, okay, Vmax is given as y squared over 8 mu times the P all over the X. So all parameters remain the same. Okay, so take note, please, this is Y squared for the maximum leakage velocity. Okay, so Vmax is now equal to Y remains 0.05 all squared divided by 8 times mu is 0.18 multiplies the PDX, which is the pressure gradient. That gives us 2.5 by 10 to the power of 7. So just like before, we are going to calculate the numerators, multiply all to the numerator. So 0.05 squared multiply 2.5 by 10 to the power of 7. So that gives us 62,500 all over 8 times 0.18 gives us 1.44. So we divide now 62,500 divides 1.44. This implies that the maximum leakage velocity is 43,43402.7 meters per second. So this gives us the maximum leakage. Okay, so the third question says we should calculate the shear stress. The third question says, that's the final question, say we should calculate the shear stress. Okay, we have to find the shear stress tau, and to do this, the Newton's law of viscosity always makes these equations and these solutions very easy. So we employ Newton's law of dynamic viscosity, and from Newton's law of dynamic viscosity, tau shear stress is given as mu du all over dy, where du simply means du dy is the velocity gradient. Du means change in velocity, dy means the thickness. So that means we can actually write this as mu Vmax all over y. Of course, Vmax is the maximum velocity. Therefore, shear stress tau is mu remains 0.18 from the question multiplied by Vmax gave us was 43402.7 all over y, which is the thickness is 0.05. So this actually gives us, this implies that shear stress is equal to. So let's obtain the multiple of the numerator. 0.18 multiplies 43402.7. So we have 7812.5 all over 0.05. So we divide that, we are going to obtain the shear stress. So we have 1.56 by 10 to the power of 5 Newton per meter squared. Okay, let me take it down here. So the shear stress tau is 1.56 by 10 to the power of 5 newtons per meter squared. So this becomes the value of the shear stress. All right, guys. So that is it for that particular question. We are moving now to the question 6, which is the final question in section 3. Okay, so we'll move down to question 6. So now we're on section 3, still on section 3, question 6, which is the final question for this 2021 examination question. So question 6a, the first question says, that's question 6a. Question 6a, it says differentiate between a local head loss and major head loss in pipe flow. Give three examples of conditions that can cause a disturbance in a pipeline. All right, so let's start with the first question. The first part of the question says differentiate between a local head loss and a major head loss. Now, the local head loss is also called the minor head loss or minor energy loss, whereas the major head loss can also be called the major energy loss. Now, the major energy loss is the energy loss that is found in a pipe due to friction. The major energy loss is the energy loss that can be found in a pipe due to friction, and there are basically two formulas to calculate the major energy loss. We can make use of the Dicey-Weisbach equation. Okay, we can make use of the Dicey-Weisbach equation. Okay, to calculate the head loss due to friction, or we can also make use of the Chassis formula all right, to calculate the head loss due to friction. So basically, head loss, the major head loss is actually the head loss caused by friction between the fluid as the fluid enters into the pipe. So the friction between the fluid surface and the pipe surface brings about the major head loss. Whereas the local head loss, which can also be called the minor head loss, are head losses caused due to different conditions of the pipe system. So we can have head loss due to sudden enlargement of the pipe. We can have head loss due to sudden contraction of the pipe. We can have head loss due to entrance or exit, or due to pipe fitting and all that. So it's actually a head loss that are caused due to lots of conditions in a pipe. So it's simply called a local head loss. Now, this same question, the question 6a, the continuation says, give 3 examples that can cause a disturbance in a pipeline. Okay, examples that can cause the disturbance in the pipeline. Disturbance in the pipeline. We can have an obstruction in the pipeline. When there is an obstruction, let's say a stone is on a pipeline, it can cause a disturbance in the flow of fluid, which leads to head loss due to obstruction. Okay, we can also have bends. If the pipe has a bend, maybe a 90 degrees bend or a 45 degrees bend. If the pipe has a bend, also that bend can also cause disturbance in a pipeline, leading to head loss due to bend. We can also have head loss due to several pipe fittings. So several pipe fittings as well can also cause disturbance in a fluid. As fluid flows, several pipe fittings can also cause disturbance in a fluid. So of course they say we should mention 3. I've mentioned a stone, an obstruction. I've mentioned a fitting, pipe fitting. I've mentioned a bend. You can as well go ahead to talk about expansion in a pipe. You can talk about contraction in a pipe. You can also talk about um, pipe fitting, several pipe fitting, right? So like these are many more. Okay, you can talk about pipe fittings and all that. All right, so you can also have inlets as fluid enters through a pipe. Okay, inlet and exit. These are all conditions that can cause disturbance in a pipeline. Anyways, that is it for question 6a. Let's move over to now question 6b. Question 6b says a horizontal pipe of 5 cm diameter conveys oil of specific gravity 0.9 and viscosity 0.1 Newton seconds per meter squared for a pressure drop of 20 kilonewtons per meter of pipe length transversed. Assuming laminar flow, first evaluate the average velocity of flow and confirm laminar flow condition. Then calculate 1. The flow rate and the center line velocity. 2. The velocity and shear stress at 1 centimeter from the pipe. And finally, the frictional drag over 100 meter of pipe length. All right, so let's pick out our parameter for that given question. Let's pick out our parameter. We are given that a horizontal pipe of 5 centimeter diameter. So we are given diameter D was given to us as 5 centimeters. So we convert this to meter simply by dividing 5 with 100. That will give us about 0.05 in meters. Okay. Conveys oil of specific gravity. So we're given specific gravity S as 0.85. Okay, 0.8, sorry. Oil of specific gravity 0.8. Okay, and viscosity 0.1 Newton seconds per meter squared. Of course, this is dynamic viscosity. Viscosity mu equals 0.1 Newton seconds per meter squared. Okay, we're given pressure drop per meter of pipe length as 20 kilo. So this is actually pressure gradient. The pressure gradient or pressure drop. Okay, pressure drop, as the question says here, that's dp, was given as 20 kilonewton per meter squared, and then they said per meter length. So always I've said whenever you're making use of the Hagen-Poisuilles equation, because we're going to use the Hagen-Poisuilles equation to solving this problem, then if they say pressure drop per meter length and the value of length was not given, you always consider your length to be equal to 1 meter. So some questions can come by saying pressure drop per unit length. So in that case, it was clearly specified that length is 1, but in this case where they say per meter of length, also take length to be equal to 1. Now, question says, assuming laminar flow, first evaluate the average velocity of flow. So the first thing to do for us from the question, it says we first of all evaluate the average velocity of flow. Now, to find velocity of flow, we have to make use of the Hagen-Poisuilles equation to calculate first for the discharge. Okay, we have to make use of the equation to calculate first for the discharge. So from Hagen-Poisuilles equation, okay, we have that pressure gradient dP all over the x is equal to 8 mu times discharge all over pi r to the power of 4, where r is the radius of the pipe and q here stands for the discharge, mu stands for coefficient of dynamic viscosity, and the pdx indicates the pressure gradient. So what we'll do now is that we are to find velocity. We know that velocity lies in the discharge, so we need to make discharge subject of the formula, find the discharge, then we can find velocity from there. So from here now, if we make discharge subject, q is equal to, we are going to have dp all over the x multiplied by, we cross multiply, this multiplies everything under here, so you have the pdx multiplies pi r to the power of 4 all over, then we divide through by 8 mu all over 8 mu. This gives us the formula to calculate for discharge. So let's compute. Okay, the pdx already is known. The pdx was given. Of course, the length is same thing as the x, and the length here is 1 meter, so the pdx here remains 20 kilonewtons per meter cube. But then let's compute it here. The p all over the x is equal to the p was 20 kilonewton. Kilo is by 10 to the power of 3, and length is 1, so it remains 1. This remains 20 by 10 to the power of 3 newtons per meter cube. That gives us the pressure gradient. So we can now solve for discharge using this particular relationship. Okay, solving for discharge now, we said the pdf, the pressure gradient, we have 20 by 10 to the power of 3 multiplied by, okay, remember now from the formula, we have the pdx times pi. Pi is 3.142 multiplied by radius, and we were given diameter of the pipe from the question. Diameter was given to us as 5 centimeter, which we converted to 0.05 in meter. So we need to now find radius. Radius is simply what? Diameter all over 2, which is 0.05 divided by 2, and that will give us about 0.025. So remember, radius squared. So radius is 0.025. We'll append that into the formula. 0.025 all, remember, all to the power of 4, please, not squared. Okay, so all to the power of 4. The pdx times pi r to the power of 4. Okay, so this divides by 8 times mu, and the coefficient of viscosity there is 0.1. So you have this. So this simply implies that discharge q is now equal to, so we obtain everything at the numerator. At the numerator, we have 20 by 10 to the power of 3 multiplies 3.142 multiplies 0.025, 0.025 to the power of 4. All right, so everything on the numerator or multiplication gives us 0.024 divided by the denominator remains 8 times 0.1 remains 0.8. So we have to now find 0.024 divided 0.8. This gives us the value of our discharge Q. So our discharge is 0.03 in meter cube per second. So this is now our discharge. Okay, 0.03 meter cube per second. That's our discharge. But the question says we should first of all confirm the velocity. So we need to now find velocity, and we know that discharge Q is actually area times velocity. And area, it's okay, from here we can make velocity subject, it becomes discharge all over area. So area itself is pi all over 4 times diameter squared. So this is now equal to pi is 3.142 times diameter was given as 0.05 all squared to the power of 4. So let's find the area. This implies that area is equal to, so 3.142 multiplied 0.05 to the power of 2. Okay, so if you divide by 4, the answer gives us 1.96 by 10 to the power of minus 3 in meter square. So this is now the value of our area. So if we know the area, we can now find the velocity. Therefore, average velocity, okay, V is equal to, say, discharge all over area, and the discharge is 0.03 all over the area is 1.96 by 10 to the power of minus 3. So this simply implies that the average velocity is equal to 15.3 meters per second. So this is the average velocity. Now, another condition in the question says confirm laminar flow condition. So we need to now confirm if truly this fluid undergoes a laminar flow. Okay, we need to confirm. So, and to confirm that, we have to employ the Reynolds number. We need to employ the Reynolds number. So Reynolds number, recall, is equal to rho Vd all over mu. So all we need to do now, we know mu, which is dynamic viscosity. We know the diameter. We've gotten our average velocity, which is this. We need to now find what? The density. But recall from the equation, we are given specific gravity. Okay, recall that S was given to us, specific gravity was given as 0.8. So if you have the specific gravity of any fluid at all, you can always find the density of the fluid, because specific gravity S is equal to density of any fluid, okay, all over density of water, which is a constant value. So from here, you can find the density of this fluid by what? Cross multiplying. It becomes specific gravity times density of water. So you have S times density of water. So therefore, specific gravity of that fluid, sorry, density of that fluid becomes specific gravity is 0.8 multiplied density of water is 1000, and this will actually give us 800 newtons per meter cube. So density of that fluid is actually 800 newtons per meter cube. So if you have this to be the density of the fluid, we can now find the Reynolds number to check whether it is laminar or turbulent. So Reynolds number is now equal to, we said, rho, which is now 800 density, times average velocity, which gave us 15.3, 15 point, is it 15.3? 15.3 multiplied by diameter gave us 0.05 all over mu. Mu is the coefficient of viscosity, which is 0.1. So let's compute the numerator. 800 times 15.3 times 0.05. So the numerator gives us, okay, Reynolds number is equal to, numerator gives us 612 all over 0.1. This implies that Reynolds number is equal to, so we'll do 612 to divide 0.1. We have 6,000, 6120. Now we notice that the Reynolds number is actually greater than 2000, and it's even greater than 4000. Reynolds number is also greater than 4000, okay, because we have here 6120. So which means this fluid is not, or this flow is not a laminar flow, it's actually a turbulent flow. So the second question says confirm laminar condition, hence it is not laminar, it is simply what? Turbulent. All right, okay, now we are starting the main question proper. Question I says calculate the flow rate and the center line velocity. So to calculate the flow rate, when they say calculate the flow rate, it actually means the mass flow rate. Okay, we are actually asked to calculate the mass flow rate. So you have to be very careful as well to understanding the question. Flow rate does not mean discharge in this time around now, unless it's a volume flow rate. Okay, that's discharge. I've already solved for discharge. So they're asking you to find the mass flow rate. Okay, mass flow rate, and mass flow rate, m dot, is actually density times discharge. This gives us mass flow rate, and we'll solve for density earlier. We obtained 800 multiplied by, we also solve for discharge and we obtain 0.03. So this simply means that the mass flow rate is equal to 800 times 0.03. So the mass flow rate is kilograms per second. This is now the mass flow rate. All right, and that same question says find the mass flow rate and the center line velocity. Anyway, center line velocity simply means divide the velocity, the average velocity by 2. That's just what it means. Okay, so center line velocity, okay, is simply v equal to average velocity divided by 2, and the average velocity give us 15.3 divided by 2. This will give us the center line velocity. 7.65. So you have 7.65 meters per second. So this is the center line velocity. All right, so the next question says, which is the final question, says calculate the velocity and shear stress, at 1 centimeter, okay, from the pipe wall. All right, now to calculate velocity, first of all, at 1 centimeter from the pipe wall, we make use of the Hagen-Poisuilles equation, which states velocity at a distance is equal to dp all over the x multiply 1 all over 4 mu multiplied by r to the power of 2 minus r to the power of 2. Now, this larger arrow becomes the radius of the original pipe given to us, and this smaller arrow becomes the 1 centimeter, which is the distance we're calculating this distance from, okay, the velocity from, sorry. So arrow becomes 1 centimeter, that's the smaller arrow. Now, our larger pipe gave us diameter of 0.05 in meters. We calculated it, so we can find the radius simply by dividing 0.05 by 2. So that will give us the larger arrow to be equal to 0.025 in meters. Now the smaller radius, which is small arrow, that's the distance we're solving from, is given as 1 centimeter. So 1 centimeter, you divide it by 100, that will give you 0.01 in meters. So this is the distance we're calculating our velocity from. Okay. All right, so if you know this, we can now plug into the equation. We know our pressure gradient, we know our dynamic viscosity, so we can now plug into this whole equation. So velocity at a distance, Vd, is now equal to, remember the equation, dp dx, which is the pressure gradient, and we obtain pressure gradient to be equal to 20 by 10 to the power of 3 multiply. Now remember 1 all over 4 mu, and that's simply 1 all over 4 by mu is 0.1 multiplied by capital R, which is larger diameter or larger radius, in this case 0.025. Okay, so you have 0.025 all squared minus smaller radius, that's the distance point, distance about, which is 0.01 all squared. All right, you have this. Okay, so the velocity at that particular distance is now equal to, so 20 by 10 to the power of 3 multiplies 1 remains 20 by 10 to the power of 3 all over 4 times 0.1 gives us 0.4. Okay, the whole of these times, let's now evaluate the whole of this together. We have 0.025 squared minus 0.01 squared. So that gives us 5.25 by 10 to the power of minus 4. So we'll now evaluate everything at the numerator. Okay, so velocity at that distance is now equal to, so we'll simply do 20 exponential 3 multiplies 5.25 by 10 to the power of minus 4, and that will give us, so that gives us 10.5 divided 0.4. This implies that velocity at 1 centimeter is now equal to, we have 26.25 meters per second. So this is now the velocity at that particular distance. Next thing, we should find the shear stress also at that distance. All right, so next, to find the shear stress, okay, we'll use the equation shear stress is equal to 4 mu v all over d, where v becomes the velocity at 1 centimeter, which we just found. That will give us the shear stress at that same distance. Okay, so shear stress is equal to 4 mu remains 0.1 and velocity at that point, we'll just obtain that now to be 26.5. So you have times 26.5 all over. Now take note, d becomes the diameter of the larger pipe, which is 0.05 in meters. So let's obtain the numerator. 4 times 0.1 times 26.5. So that gives us 10.6 divided 0.05. So this simply implies that the shear stress at that distance is equal to, you have 212 newtons per meter squared, and that gives you the shear stress at 1 centimeter. All right, guys, so that's it for that question, and that's it on 2022 past question on fluid mechanics for all Rivers State University students. So I hope this actually helps you succeed in your exams, and I pray and wish you guys all the best. Thanks and cheers.